Hey guys, and welcome back to Mr. Cole's Classroom. Today we're looking at free body diagrams. Mr. Cole, or of course, we could always say the artist formerly known as Turdferg67 here. Anyway, as we take a look today, this subject of free body diagrams, essentially what we're looking at, I'm going to assume you've seen these in your book or your teacher, and you're just not 100% sure how these come about. So let's get that started today. And I'm going to do my first one. I'm going to take a look at Bernie Sanders having a nice, comfortable, relaxing, but cold yet day sitting in his chair here. Before we do a diagram on him, though, I'm going to do something. Bernie's got what's known as a normal force acting on him. So let's take a look at this concept of a normal force. I'm going to do a surface here, and then usually what you will have when you're doing a problem like this, typically the first problem you ever see is like a block sitting on the surface. So let's kind of do that because I want you to understand what a normal force is. So usually when I'm telling students to draw these, the first thing I tell you to do is this. So let's look at a block because Bernie is the same as a block, and no jokes being made here. This is just an example that I'm using. When I'm looking at the block, usually the first thing I tell students to do is this. I tell them to go ahead and look at the force of gravity here. Some teachers will make you write FG for this. Some teachers will make you write FW for this. Some teachers will let you use W, and then some teachers will let you skip and go straight to MG because, well, let's face it, all of these are true. If you're in my class, I'm perfectly cool with you just going straight to MG. So now here's the thing that works against this. You probably saw your teacher do it. You draw an arrow up. Most teachers either write FN. I like writing lowercase n, and all that represents what's known as a normal force. So that's a normal force. And then there's a lot of teachers have a bad habit of saying, well, this is a Newton's third law scenario. I'm going to go ahead and do something here. Do not say that, please. I'd ask for you, please. This is not an example of Newton's third law. Yeah, these just happen to be equal and opposite, but that's not what's taking place here. The normal force is actually created by particle interaction. So, like the surface that this block is setting on, and I'll do this real quick because you kind of need to understand this because I don't want you showing up and talking about this as equal and opposite reactions. That's not what this is an example of. Here's the thing, as this block sets on the surface, these particles in the surface, they are interacting with each other. So if you can imagine like all these connected by springs, and Pascal actually makes an object like that where all these connect by springs, and all these forces, all these particles are interacting with each other, and they're also interacting with the block as well. And so all these forces combine to make this normal force, which in this case is equal and opposite, but that's not Newton's third law that's going on here. It's just that these forces are balanced because this object is remaining stationary. And so the word normal itself is actually referring to, see if I can do this. I'm looking for a color I haven't used, like green here. The word normal itself is actually this 90-degree angle that you see because the normal is 90 degrees to the surface that the object's sitting on, and that's why we make those references. So, for example, if let's just say, let's do this. Let's say an object was on a hillside, such as this. If the object was setting on the hill, we would, give me a red, please. We would do a MG straight down upon the hill, and then we would draw our normal force at 90 degrees to the surface of the hill. One time I gave our, not one time, I used to do it every year. I used to give students a problem always where you had you had a student that was at some amusement park ride, and he was riding or she was riding. Sure, well, there we go. Whichever way you want to swing this one. They're riding on this ride, and the bottom falls out, and they stick to the wall. Well, in the case of that problem, what happens is this: the normal force is 90 degrees to the surface that they're pressed against. So the normal force is that way. The student has an mg going down, and then what's keeping them to the wall is a frictional force that here I'll call Fs. By the way, your teacher may use f for friction, so either way that they go at it. So using that, let's go back and take a look at Bernie, for instance. So Bernie would be this example here. Put a big dot. Everything in physics, you can be a great artist as a dot. So in the case of Bernie, he would have his mg down, and since he appears to be sitting there balanced, that means when I draw this diagram, I would do an mg down. And again, your teacher might use FG, might use W, might use FW. There's so many options, it's hard to choose. And then normal force for me, I do a little lowercase n like that. And again, your teacher might choose to do Fn. We're not going to talk about it anymore though, okay? So if these forces are balanced, in other words, he's not moving, he's static, then I draw those equal lengths. So let's take a look and see if we can do. So here's somebody pulling on the car. And so the first thing I always tell people to do, hey, do your weight first. So do an mg. Let's get our weight going straight down. It's setting on a surface. So at 90 degrees to that surface, we have a normal force. There's a rope. Whenever I see a rope attached to something, I always call that a tension. Some books will call that an FT. So again, I always just write the letter T, and usually it'll either give you an angle or ask for it. Now, if this surface was frictionless, in other words, mu equals 0, then we would be done. I'm going to assume that there's probably a little roughness here. So let's draw I'll do a somewhat smaller arrow backwards here, and I will write F. Now, depending on the scenario, there's two types of frictions. Fs for static, so that just means it's not moving, and FK, I'll be the first one to admit a lot of times I'm lazy and I just write the letter F. Your teacher, though, might write little f. So just be aware of all these little intricacies of this. All right, skydiver. The reason why I threw the skydiver in, I see students over and over, they immediately go, yeah, I got this MG, and then they go, oh, and there's a normal force. Question, pop quiz. What is this skydiver standing on that would give him a normal force? Well, nothing. So there's not a normal force working back against a skydiver, but there's a drag force. And I'm actually going to use the letters FD for that drag force myself even. So when we do the skydiver, we would do an MG down, and then with the skydiver, and now it kind of depends. If the skydiver was at constant velocity, in other words, if he was at constant velocity, there was no acceleration on this guy, then I would try and put these two somewhat equal to each other. However, if I was looking and the problem said he was accelerating down, I would do my mg down, and I would draw a somewhat shorter FD drag force up, and I would do that to show that the forces were not balanced on that skydiver. And some teachers are very picky about that subject. Let's look at the penguin on the sled. To begin with, let's see that he's on a frictionless hill. And so the frictionless hill, we would draw an arrow. Again, this is always the easiest, safe thing to do. Any diagram, MG straight down, the penguin is on the hill, so we would now draw a normal force at 90 degrees. And if that's all there was, I always like taking this picture and kind of tilting my head, as it were, and straightening it out. And that means I kind of draw it with the normal force on the y-axis. This just makes it easier for you when you're doing your sum of the forces or net forces later. and then there's my MG. Now, if this hill is frictionless, and there is an angle, but we're going to talk about that in a second. If the hill is frictionless, this would be it. If the penguin was like sliding down the hill and there was a friction, then we could write like a small FK working back against it. The thing that always gets students is this angle, it's kind of odd, but typically we always use angles off of the x-axis, but whenever we work a problem on the hill, we always end up doing it on the y-axis, and here's the reason why. So if you take a look and let's draw a hill, and now here let's do this. Let's kind of base that out and give me a red line. How about a dashed red line with an arrow? Boom. And it's going the wrong direction. So, hey, that's not bad. I can still fix that with a mouse, right? So let's say there's an object on that hill. I just use the straight lines because I want you to gather something for a second. If there's an object setting on this hill, if there's an object setting on that hill, then we look at that MG that's going straight down. Now, I want you to notice something. This makes a right angle. So the problems usually tell you the angle of the hill. Now, if you take a look, this angle up here then would be 90 minus theta. So that means, here, if we kind of get our y-axis on this hill, then this back angle is the same as the angle of the hill. So you're going to see that quite a bit, and then you'd have your normal force at 90 degrees again to the surface of the hill. So that's just whatever you see, we always use this angle in the case of like objects on hills. All right, I know we are crashing through massive amounts. So here we got the same thing. We got a crate on this hill. We would draw our MG straight down. And sometimes I like drawing on my picture first. We would have don't ask why I just drew this massive normal force. And then somebody is pushing it. The guy looks like he's pushing it straight up the thing. So I would usually just do an F. Some people do an FA. I'm going to wager that's not frictionless. So we'll do like a little, that's not a lowercase letter F, is it? Little F. And then we'd have this angle from the hill, which is the same as the angle of the ramp. So let's draw this over here straighten out. Let's do the normal farce first. We got this N, the MG. This thing looks pretty heavy. So we got an MG going backwards. The angle is the same angle that the incline is at, as we just discussed. We would have a F, and assuming he's actually moving it, maybe an FK going back. And then this guy looks like a beast. So we'll go ahead and give him, some teachers will do a force, some teachers will do FA for force applied, whatever you want to call it. Whenever I have somebody pushing, I usually just call it a force like that. If there was a rope pulling it, I would have called it a tension. Hopefully you are totally killing it, because this is our last one. This is what's known as an Atwood's machine. It's probably one of the most common problems that if you will do this problem where you have two buckets. And guys, the easiest way to do this, and if you notice, they're really very easy. I've got an MG for this guy, an MG for this one over here, and then there's a tension on this one and a tension on this one. The only difference between algebra-based physics and calculus, or even just a little better frictionless class, it really kind of boils down to, is there friction in that pulley? So here's the thing. If this pulley is frictionless, so there is no no friction in that pulley, here's what's cool. This tension is the exact same on each one of these. So when I go to do this, I would draw a tension straight up, or an FT, if that's your teacher's flavor. And I would draw, but now I'm going to do I'm going to call the one on the left an M1G down. And when I do the one on the right, you can probably read my mind. We will call it an M2G so that we can differentiate between these two. And we'll call T. If you're wondering, Mr. Cole, what is the difference if you had a mu in here? If you had a mu, then you'd have a T1 and a T2. The tensions would be different, and we would also have to do a calculation for what's known as torque, but you're probably not there yet. If so, I've got videos where I solve buckets problems like that with the torques in there, but that's where that comes into play as with torque. And so it's not it's very possible for algebra-based physics to do that. There's no calculus involved. So it just depends on your teacher and what they're up to. Well, guys, that is the end of this presentation. I hope you're going a long ways with it. I'm going to do a next video that goes with this where we calculate the sums of the forces with these. So 15 minutes, guys. Thanks for watching. You guys stay happy, frosty. Enjoy physics. Hey, do something, guys. Love y'all.